team? Hope everything is well. And this is our another class on physics, and we're going to be talking about electric potential and electric potential energy. To begin, let's talk about work, because it's a very big part in our subject here. So work is equal to force times distance times cosine theta. The distance and the force have to be parallel to each other. So for example, if we have an inclined plane, right, and this inclined plane has an angle theta, this distance right here to this distance right here is d. We have a block that's starting all the way at the bottom, and we have a force that is horizontal, and it has an angle when applied to the block. That angle is theta. Okay? Because we have to make it parallel to each other, have to make it parallel to the distance traveled, and this distance, once you start pushing it, it starts traveling a distance d all the way up here. Then we need to find the component that is parallel to that distance. So if I make a coordinate axis, now the x-axis turns as the distance that is being traveled. And I have to find force cosine theta. Thus, work equals force times distance cosine theta. That's where the cosine comes in, to ensure that both the force and the distance traveled are parallel to each other. Okay? That being said, we can rewrite this as work equals initial final distance, the initial distance, final distance, times force, times the infinitesimal distance traveled. So what an integral does is it takes from the initial and the final distances, it takes an infinitesimal distance, a very small, minute distance, right? That's what this is right here. That's what the work that we're calculating. But with integrals, what it does is that it picks from the initial all the way to the final, and it basically picks up all these small infinitesimal lines, and we make it up completely, summing it all up and making it completely understand that all this from the initial to the final, we can find work. That is basically what it is. When we integrate, and you will see it a lot clearer, we can find that work is equal to force times distance r final minus force times distance r initial equals to work. Okay? Now that we covered that, let's talk about potential energy. So potential energy is the energy that can be used to do work. It can be used to do work. It is energy due to position. So if we have a ball, and I love my balls, that's sounded wrong, but if we have a ball and we have a height here, and this over here, the surface right here is 0, then at this point, at this height, if this ball stays there, then it has potential energy, but it hasn't done work yet. Because remember, it's the ability or the energy that could be used to do work. So we have mass times gravity times height. And potential energy is denoted as U. You see U here, you see U here in your physics reference card for your own reference. So keep that in mind. Now, if I drop the ball, though, if I drop the ball and it's coming down, now there is a change in potential energy. I am losing potential energy as it's dropping down. But in losing potential energy, I gain work. So that's why you see this equation right here, and let me highlight it. This equation right here where it says work equals to negative change in potential energy. So work equals negative change in potential energy. And we can see it too. So like let's say the change in potential energy is U final minus U initial, right? U final is 0 because once it drops, the height is 0. But then U initial is mass times gravity times height. And we are left with negative mass times gravity times height. That negative means that we are losing potential energy. However, because we're losing potential energy and it's coming down, it is doing work, and that work is positive. So that's why there's a negative right there. And when you multiply negative change in potential energy, it will give you a positive work. And when it comes to either potential energy, kinetic energy, or work, we always denote it in units of joules. Okay? Now that we took that apart, I'm going to erase this. I'm going to erase this, and I'm going to talk about electric potential energy. So electric potential energy describes how much stored energy a charge has when moved by an electrostatic force. What I mean by that. So if we have two particles, we have a positive particle, positive charge here, and we'll name it Q1. And then we decide to put a charge right here, another positive charge here, and we will name that Q2. Right? Let's do the electric fields for Q1, just for the heck of it. Very nice. Okay. Now, if I decide to move Q2 from its distance, and let's call this distance from here to here, let's call it infinite. You know, like that, it's infinitely far away. Okay? That R, let's put it as R initial, as infinitely far away. And then I decide to bring this Q2 ever closer to Q1. Right? So as it's getting closer, remember that two of the same signs are repelling. So it is, as I am putting Q2 closer, it is actually experiencing a repelling force. And that repelling force gets more intense as they get closer. So right now it's really much pushing away. Remember, electric potential energy describes how much stored energy a charge has when moved by an electrostatic force. So the closer they are, the greater the potential energy, electric potential energy, because now I have a force, electrostatic force, that is pushing this way because I am getting ever closer. And this distance right here, let's call this distance as R2 or R final. R final. Let's put it like that. Okay? We are finding out the electric potential energy, so let's do this. We know that work is equal to force times distance times cosine theta. However, because we're dealing with electrostatic forces, we can change this force into the equation that they give us here. We can rewrite it as K times Q1 times Q2, charge 2, over R squared. And let's write down final. All right, wait, actually, let's even do it. Let's do this even more interesting. Let's do it the way that the integral has it. Work is equal to, it's the same deal, initial, final, work times the infinitesimal distance r. And then when we integrate it, we have force r, final, minus force r, initial. We change this into electrostatic forces. We're given Q1, Q2, times Coulomb's constant, R final squared, minus K Q1, Q2, over R initial squared. And I forgot one extremely important thing is to multiply it by R final here and R initial here. Very much, you see, this is the distance. This is the distance. Give me a second. There we go. This is F. This is the distance. This is F. This is the distance. Very similar to, or very much the same to, work equals force times distance times cosine theta. Since we are dealing with two electrons, or not two electrons, but two charges that are basically parallel to each other, cosine would be of 180 or 0. So it would basically be just 1. Cosine of 180 is -1, cosine of 0 is 1. Yeah, that's why we don't use cosine theta in this situation. That being said, all of a sudden we start scratching this. Okay, so we have these two, they cancel out because we have r squared at the bottom, but r at the top. So now we are left with just these equations, which is the same equation as the electric potential energy equation. And we're left with U final minus U initial, and that would equal to work. Now, notice that these are absolute values. So that's why when it comes to the negative VAT sign, you don't have to worry about that. However, I'm just showing you the relationship between work and the change in potential energy. In actuality, if you wanted to take it the other way, now you have to definitely consider that when it comes to this equation, notice that they don't have absolute values, right? So it would be, to get work, it would be work equals negative change in potential energy, and you would go work equals to negative parenthesis the electric potential energy of final minus the electric potential energy of initial. And that, multiplying that, would give you work. Okay? So, again, as you're holding it there, it means that, or as you're holding it here, it means that you have stored energy in that charge that once you let it go, for example, it shows like the energy that it uses, that it can be moved by the electrostatic force. So that's what it means. Okay, I am going to do this problem from the actual required problems, just so you can see how to apply it. So it says, to form an atom, a proton is fixed at a point and an electron is brought from far away to a distance of this. And I'm going to call the distance r. Let's put it r final. And then it says it's brought from far away. So that other one is r initial, and r initial is infinite, because it says from far away. So we would assume that it comes from an infinitely far away position all the way to distance of 0.529 10 to the negative 10 meters. Okay? The average distance between the proton and electron on a hydrogen atom. Okay, fine. How much work is done? So looking at your equations, you can do it two ways. You can use your equations here. I'm going to bring this up, copy, and paste. You can use your equations here, and it shows that you can do it two ways. You can find work due to the negative change in potential energy, or you can find work using this equation right here. In your solutions, they go about this route, the integral. But they also show that if you do it under the change in potential energy, it will give you the same answer. So let's start off by doing it the easy way. Work is equal to negative change in potential energy. And then we go on and say, okay, so if work is equal to change in potential energy, then that means that negative U final minus U initial is equal to work. Looking at our equations, right here, that's our equations. If we decide to go with the direct route, we go minus U times K, columns constant, times this charge 1. And we'll call charge 1, let me just put charge 1 is the electron. Charge 2 is the proton, right? It's a proton. So we'll put it proton P, okay? So Q1 and Q2, distance R. And this is distance R final, because that's what we're dealing with at once we get to the final position, right? But then at our initial position, since it starts at a very far away place, it's still the same charges that we're dealing with, but at a different distance. And we would go as over infinite, right? In close parentheses. Because it is over infinite, when you divide something over infinite, it is indefinitely small, infinitesimally small. So because infinitesimally small, you can assume that this is actually 0. And all you have left is work equals to negative columns constant times charge 2 over R final. And R final is that distance of 0.529 times 10 to the negative 10 meters. Because one is positive, one charge is positive, and one charge is negative, this will end up being a positive work. And I'm going to write it positive work in joules. Okay? So that is the easy route. We can also do it the more interesting route, which is work equals the integral of infinite distance, the final distance, force, times the infinitesimal distance between our final and infinite. And then when we integrate it, we are left with force times our final times, minus force times our initial, in this case it's infinite distance. And if we decide to convert that, we have the equation right here. And we can rewrite it as K Q1 Q2 over R final squared times R final minus K Q1 Q2 times over infinite times infinite. Right? Because infinite is the initial R. And you can cancel, and infinite squared. So it's infinite squared, infinite squared. So now you can cancel this. This one right here, you can cancel it. And there's only now one at the bottom. The same thing goes with our final. You can cancel this, and now there's only one at the bottom as well. So work, once you do this, notice that work is positive because these two, charge 1 and charge 2, are absolute values, so it turns positive. And then all you have left is Q1, Q2 over our final. And voila, you have positive terms here and a positive term all the way over here when you did the electric potential energy route. So you see how they're connected, right? Understanding that the force, finding electrostatic force, finding the work, and then understanding the change in potential energy is work as well. Those connections between block 2 and block 3 start to converge to make this beautiful product, of course. So this is one problem, and this is a long video. I admit this is a long one because these are topics that are extremely important. So now let's talk about electric potential, And electric potential, let me write it down. Electric potential is just a number associated with points in space. So that's why I wrote down these space. Right now, this is completely and utterly empty. Nothing's going on, right? However, if I decide to put a charge right smack in the middle of this, and it's positive, now there's electric potential. So electric potential also depends on the distance. So right here, you would see a high electric potential. And electric potential is denoted as V. And V is equal to, in units, joules per coulomb. So it has energy, it has the potential to have energy, but you have to have another charge to actually have energy. The way it works is that you cannot have neither an electrostatic force or energy if you don't have another charge reacting to the charge that you place right smack in the middle. You have to have another charge. But you can figure out what could be possible if you did put a charge there. So you can understand the energy that you can take, that you can have if you put a charge right here, as well as the energy that you can have if you put a charge right here by understanding the electric potential. The farther you are, the lower it is. The closer you are to the charge, the higher the electric potential. Okay? We can find this by using the equation of the change. Let me not use green anymore. The change in potential energy is equal to charge times the change in volts. And we can find this, not volts, in electric potential. Right here. So, let's say that right here in this spot that I'm circling, we understand because of this charge right here, I want to find out the electric potential in this spot. So I would go make a line from where my charge is at all the way to my reference point, and that distance is R. Right? R. But I want to find the electric potential, so I need to multiply my column constant by the charge that's making the electric potential over the distance R. So I have to have that charge that makes the electric potential over this reference point right here. And thus, I have found my electric potential. But in order to find potential energy, I would have to multiply it by a charge. So if I decide to put in a charge right here, and that charge is plus 2 coulomb, to make it as simple as possible, right here, boom. Then now I can actually solve for the electric potential energy. And electric potential energy is, for this situation, is, let me put it in black, U equals Q, which is the new charge, which is 2 coulomb, times V. Because right now we're only looking at that one. There's no change in electric potential. We're only looking at that one, at that specific spot. Okay? Electric potential. And that's how you find the electric potential energy right there. That's how we understand that we have, like how much energy do we have in any spot within this space that I created right here. Okay? Now I want to cover something important before we go into the problem that I have for you here. Electric potential is not volts. It can be volts if it's the change in electric potential. And we write down the change in electric potential is actually equal to voltage. And they could have the same units, which is joules per coulomb. However, when we distinguish the difference between electric potential and voltage, that's when we go and say that this voltage is actually volts, or V. So you can understand the differences between those two. I want to do one last thing for you before I actually go so you can understand like how everything is meshing. We talked about last class electric fields. In electric fields, we can write them in terms of change in potential, electric potential as this. Change in electric potential is equal to negative initial times final times, or the integral of the electric field times the infinitesimal distance r. And let me rephrase that because I said initial times final. No. Between the initial, the integral between of the electric field between the initial and the final times the infinitesimal distance r. Doing this is just a product right here of the original work equals the integral between the initial and final position of F infinitesimal distance r. Okay? What I mean by this is that once you start converting, look at what this equation is. The one that I'm highlighting for the PRC. We change it, work equals Q, charge, times the electric field, times the infinitesimal distance. If we bring Q to the other side, and Q is equal to, let me continue my work here. Because what we're studying is not Q, but the electric potential field, so Q would be a constant. We would be left with final times E2, or electric field times distance, or not distance, but times the infinitesimal distance r. Now look at what's going to happen here. We have the negative change in potential energy over Q. That is the same equation that we have here. You seeing where this is going? If we change this value to this one, now we have change in V, Q on the bottom, they cancel out, and we bring the negative to the other side, we have negative integral of E, or electric field, times the infinitesimal distance r. And voila, you have the same equation right here. They are all connected, and all you need is simple understanding of algebra to get to that conclusion, so you can use all tools to your disposal for when the T comes in. Now that I explained this to you, I want to touch on an example problem, which is very similar to one of the problems that was on a previous WPR that I wanted to talk about. It says two particles are held in the following configuration, and this is for electric potential. You have two charges, Q1 and Q2. The difference between electric potential and electric fields is that electric potential is a scalar value, whereas electric fields is a vector value. Notice that in electric field, and I'm going to erase this, if I was told that I needed to solve the electric field with respect to point P, I would have picked up, said, okay, so this is Q2 is a positive charge, and understanding that electric fields come outward of positive charge, I would have written a line from here to here, and there's an arrow. So now there's direction. There's magnitude and direction in this electric field. The same thing goes for my negative counterpart, which is a charge 1. Since I know that electric fields go inwards into negative charge, then I have another direction. If I would written a coordinate axis, then I would realize that if I was studying the electric field in the x direction, I would go negative electric field 1, which is composed of charge 1, because it's in the x direction, completely horizontal, plus electric field 2, because it's going in the positive x direction, times some cosine of the angle. Define that. That's how I would solve it. And I would then have to do the same for electric field in the y direction in order to find the magnitude of the electric field overall. And this is for Rob. Rob, if you have electric field and you're trying to find the magnitude of the electric field or the unit vector of the electric field, you would go electric field in the x direction plus electric field in the y direction. Voila. Done. The unit vector electric field. So that's how you would do it if it was an electric field and it was a vector. However, lucky for us, when it comes to electric potential, we don't really care about that. We don't really care about the direction. All we care about is the electric potential at P without understanding the direction. We just need the magnitude, and we just need the actual distance between the two. So this is actually, when you're given 3 and 4, you do the geometric stuff and you'll get 5, but I'm going to call this R2. And this right here is R1. All you have to do to find the electric potential in P is write K times the electric potential of 1 over R1. Or K, or column constant, times the charge 1 over R1 is the electric potential with respect to P with a charge 1. Plus K, Coulomb's constant, times charge 2 over R2. That reference point. That is the important part. And voila, you just solved for the electric potential, and like not electric potential energy, but the electric potential of in reference to point P. I'm trying to do the answer. Here we go. Answer. Done. You are done. That's how simple it is. This is a previous value PR problem. Don't wrap your head too much around electric potential. However, now we're going on the second part. Calculate the work done by the electric field to bring an additional charge of Q3 from an infinitely far away to point P. Again, do not panic. So it's saying now that we are including a negative charge, Q3, right here, right in reference point 3. And it's saying from infinitely far away to point P. So the work done. First, we know that work is equal to negative potential energy. We can go this route. We also know that potential energy, the change in potential energy is the charge at that reference point times the electric potential at that reference point, the change in electric potential at that reference point, and that will give you the change in potential energy. Now that we know this, we can rewrite it as Q times electric potential of P, because that is where it ends. From far away to point P. That is where it ends. But if you want to try to find the electric potential of from far away, you would have the charge. I'm not absolutely sure what charge, but it is infinitesimally far away. Because it's infinitely far away, this would go to 0, and all you have left is the electric potential at point P. So now all you have to do is multiply the charge that was given, charge 3, times electric potential at point P, and you get the change in potential energy. But you're not done. You have to still find the work. And the work is negative the change in potential energy, the change in potential energy. Oh my goodness, I think this video was super long. But it covered electric potential, it covered electric potential energy, it covered the different varieties that you might be facing when it comes to electric fields and how you deal with electric fields in terms of electric potential and electric potential energy. This was a great class. I hope that you use this resourcefully. I know that some of you are going to be fast forwarding it, and that's completely fine. But if you ever get stuck in understanding the conceptual stuff, I think I did a pretty good job covering like all the aspects that are important for you to be successful in the team. In any case, it's been a pleasure. I hope that you enjoyed this video, and I will see you later on. Have a good night. Bye-bye. Bye.